Hi everyone, welcome back to ChemHelp ASAP. In today's video, we are going to be doing a titration, and specifically we're going to do a strong acid titrated with a strong base. Let's get started. So here is our titration. We have a 15 milliliter sample of 0.15 molar nitric acid, and we're titrating it with a 0.1 molar solution of sodium hydroxide. So again, strong acid, strong base. Here are your basic questions that you're going to ask in most titrations. First, you want to know how many milliliters of sodium hydroxide you're going to need to reach the equivalence point. Then you want to know what is the pH at the start of the titration before any sodium hydroxide is added. Next, what is the pH 5 milliliters before the equivalence point? Then what is the pH at the equivalence point? And finally, what is the pH 5 milliliters after the equivalence point? It's a lot of calculations. Before we start any actual calculations, I want to get a balanced chemical equation. So nitric acid plus sodium hydroxide is going to form water and sodium nitrate. This is following the general rule of an acid reacted with a base gives you water and salt. Another way to think about this is also a double replacement reaction. Either way, it is important always to start with a balanced chemical equation. Now we're ready to figure out our calculation for A. How many milliliters of sodium hydroxide are needed to reach the equivalence point? Well, we're going to do stoichiometry here, right? So we need to get to moles, which we do not have at the moment. We have concentration and we have volume. So how many moles of nitric acid am I starting with that need to be neutralized or need to be reacted with? All I need to do is take my concentration of nitric acid and multiply it by how many liters of solution I have. Notice I did change this to liters. The original problem gave me 15 milliliters, but again, simple conversion, you just move the decimal 3 places to the left. So I am starting with 0.00225 moles of nitric acid. So remember, what is the equivalence point? This is where moles of acid equal moles of base. This is just another reason why I wanted to get those moles of acid. So taking my moles of acid, I'm going to use my mole ratio from my balanced chemical equation, and I'm going to convert this into moles of base or moles of sodium hydroxide. Of course, I need to get all the way to milliliters here, so I'm going to use my concentration of sodium hydroxide, which the problem gave me, to convert from moles of sodium hydroxide to liters of solution. However, I have one more step because my problem asked me for milliliters of sodium hydroxide, so I just convert my liters into milliliters, and that gives me 22.5 milliliters of sodium hydroxide. Now, these calculations are pretty simple when we have just this one-to-one stoichiometric ratio, which you very often have in acid-base reactions. However, it is not always the case, so make sure you're always starting with your balanced chemical equation. All right, so that answers our part A. Let's go on to part B. Okay, so part B is what is the pH at the start of the titration before any sodium hydroxide is added. So we just have our acid in solution right now. So nitric acid is a strong acid, meaning it's going to form hydronium and nitrate. Again, this is not an equilibrium, it's just a right-hand arrow. This makes our calculations much easier. So remember, to get to pH, we need concentration of hydronium. So starting with my concentration of my nitric acid, I just use my mole ratio to convert that into moles of hydronium, and here is my concentration of hydronium. So in a 1-to-1 ratio, your concentration of acid is your concentration of hydronium. It's fabulous. Now I just need to take that into my pH equation. So pH is just negative log of concentration of hydronium, so negative log of 0.15 molar, and my pH is 0.824. Before we leave this calculation, we just want to do a little bit of a reality check. We have a strong acid in solution. Does it make sense that our pH is very low? Yes, it does make sense that our pH is very low. Okay, so part B wasn't so bad, right? Let's go on to part C. Okay, so part C is what is the pH 5 milliliters before the equivalence point. So this is why we determined where the equivalence point was before we did any other calculations. So the equivalence point was at 22.5 milliliters. Again, that's what we calculated in part A. So 5 milliliters before the equivalence point is going to be 17.5 milliliters. Remember, we've added sodium hydroxide. So we've added 17.5 milliliters of sodium hydroxide to our initial acid. I always like to make sure I have my balanced chemical equation. So here again is my balanced chemical equation. We need to do stoichiometry. So just as a refresher, we've actually already done this calculation, but again, we started with 0.00225 moles of nitric acid. Now, how many moles of sodium hydroxide have we added at this point at 17.5 milliliters? Well, we're going to take our concentration of sodium hydroxide and we're just going to multiply by how many liters we added. And that gives us 0.00175 moles of sodium hydroxide. Again, this liters came from these milliliters. I just moved the decimal 3 spots. Now that I have moles of both my acid and my base, I can do my stoichiometry. Now for these calculations, I like to set up a little bit of a table just to help me keep track of what is being consumed and what is being formed. It looks a little bit like an ice table, but again, this is not an equilibrium, so this is not a true ice table. But I do put my chemical reaction at the top, but instead of using ICE, I use start, used, and what happens at the end. So I started with my 0.00225 moles of nitric acid. I'm also starting with my 0.00175 moles of my base, and I have no water and no sodium nitrate. So how much am I going to use? Well, I'm going to use up all of whatever my limiting reactant is. Well, in this equation, remember, we have a 1-to-1 stoichiometric ratio. So my limiting reactant or my limiting reagent in this situation is going to be my sodium hydroxide. It is going to get used up first. So how much I have used is determined by my sodium hydroxide. This is going to go down to 0, which means I have this many moles of nitric acid left, but I've also formed some water, which we don't really care about, but you might care about how many moles of sodium nitrate you formed. Again, I just use this table to help me stay organized in my stoichiometry. So now I know how many moles of my excess reagent, my nitric acid I have left, and I do know how many moles of product I've formed. What am I trying to get at again? Oh, that's right. I'm trying to get at pH. So what I really want is I want concentration of hydronium ion. That is going to be determined by my concentration of my acid, but right now I have moles, so I have a little bit of work to do. To convert moles to concentration, I need to know my total volume of solution. That is going to depend on how much acid I started with. So I started with a 15 milliliter sample of acid and how much sodium hydroxide I've added. So I've added 17.5. That means at this point, my total volume of solution is 32.5 milliliters. Now I can get my concentration. So my stoichiometry gave me how many moles of acid I have. I just calculated my total volume of solution, again, just converting from milliliters to liters. So my concentration of nitric acid is 0.0153, which again is my concentration of hydronium. Those are equal. Because nitric acid is a monoprotic acid, so that's a 1-to-1 stoichiometric ratio. So now I can just plug into my pH equation and I get a pH of 1.813. Again, makes sense. I have excess acid in this solution. I don't have as much, so my pH should have gone up a little bit, but I should still be well in the acidic range for pH. That's part C taken care of. Now let's do part D. So part D asks, what is the pH at the equivalence point? Remembering, equivalence point is when moles of acid equal moles of base. So just reiterating, here's our moles of acid we started with. Here's how many moles of base that we have at the equivalence point. I'm going to use my table. It just helps me keep organized. So here are my moles of acid reacted with my moles of base. Of course, these are both going to go to 0. I can also predict how much product I formed. So now on to the pH. Well, I have a little bit of difficulty here, right? I don't have any excess acid or excess base. My salt I have formed, but sodium nitrate has no acid-base properties. So what is driving my pH then at the equivalence point? It's your water. So here is the equation. This is actually the autoionization of water. This is what is going to drive your pH at the equivalence point of a strong acid and a strong base, because they form a salt that has no acid-base properties. So again, I need to get this concentration of hydronium, but this is in pure water. So my concentration of hydronium is just 1 times 10 to the negative 7th, which I can plug into my pH calculation, and I get a pH of 7, which is the pH of pure water. But this is why you get a pH of 7 when you have a strong acid and a strong base, because water is the only thing that is driving your pH. I think it's pretty cool. Okay, that is part D done. Let's go on to part E. So now we want to know, what is the pH 5 milliliters after the equivalence point? So the equivalence point at 22.5, we're adding 5 milliliters. So now we're at a total volume of 27.5 milliliters of sodium hydroxide that has been added. I still like to keep my balanced chemical equation up. And just for reference, I'm keeping my moles of acid. You've seen this calculation multiple times now, but remember, this is how much acid we started with, so that is not going to change. It's just how much has reacted. However, my moles of base are changing because in a titration, I am continuously adding base. So 5 milliliters after the equivalence point, I have added 0.00275 moles of base. Back to the table that I like so much. Here again is my start number of moles of acid. Here's my start number of moles of sodium hydroxide. Again, 5 milliliters after the equivalence point. What is my limiting reactant? Well, it's switched. Now my moles of acid is going to run out first. So for how much I've used, that is driven by my acid. So my acid is going to go down to 0 moles. That means I have a little bit of extra sodium hydroxide left over. And yes, I've formed some product as well. But what is driving my pH 5 milliliters after the equivalence point? It's this excess base right here. So I need to get this moles into concentration. To do that, I need to know what my total volume of solution is. So my total volume of solution, I started with a 15 milliliter sample of acid. I have added 27.5 milliliters of base, so my total solution volume is 42.5 milliliters. Remember, during the titration, you are continuously increasing the volume of your solution, and that does need to be taken into account. Now that I have moles and I have volume, I can calculate concentration. So I have 0.0118 molarity for my sodium hydroxide. Again, that is also my concentration of hydroxide. Those are in a 1-to-1 ratio. So I am going to calculate my pOH first, because again, I know my concentration of hydroxide. So plugging that number in, I get a pOH of 1.930. Now the question asked me though for pH, so I need to switch that from pOH to pH, but thankfully that's a really easy calculation because pH plus pOH equals 14, so I get a pH of 12.070. Again, I always like to do a reality check. Does this make sense? And yes, I have excess strong base in solution. I should have a very high pH. A common mistake I see students make at this point is when they calculate pOH, they think they've calculated pH because they've done the negative log of a concentration. But that's where that reality check comes in, because if you have a pH of 1.93, when you have excess sodium hydroxide in solution, hopefully if some red flags start waving there, you cannot have an acidic pH if you have just a base in solution. So just always make sure you're doing that reality check. Now that we have all these numbers, let's see what this titration curve looks like. Okay, so here is our titration of a strong acid with a strong base. Specifically, we've done nitric acid with sodium hydroxide. There are a couple of parts of this titration curve that I want to point out. So where did we start? Remember, we started at a pH of less than 1 right here. And before we got to the equivalence point, so remember when we were 5 milliliters before the equivalence point, we still had a very low pH. You can see that the pH stays pretty low and then it shoots right up to the equivalence point in a very small range of volume of sodium hydroxide added. Now, once we reach the equivalence point, we calculated that we have a neutral solution, so our pH is determined by water. That gives us a pH of 7 at this equivalence point. And then once we're past the equivalence point, and again, if you look at how much you're changing on the x-axis, you're not changing that much before you're up here at a pH of like 12 plus. So you're going to have a basic solution after the equivalence point where your pH is just determined by your excess base. So these titrations of strong acids and strong bases will have very clear equivalence points, and you're going to hit that equivalence point really, really quickly with just a little bit of base added. And once you get close to the equivalence point, if you're monitoring pH, you're going to see it jump dramatically, which is why when you're trying to get good numbers around the equivalence point, you want to be adding at least drop-wise, but honestly, if you can split those drops close to the equivalence point, you're going to get much better data. I hope this helps you in your next titration, and thanks so much for watching.